Okay, everyone, good evening. My name is Rick Baldridge. I'm the Vice President of the Peninsula Astronomical Society, and we're very excited to have you all join us this evening for our August virtual meeting, our second one ever, featuring Dr. Elinor Gates from Lick Observatory, and I'll get into details of her talk a little bit later. Wanted to give you a quick rundown of some of the, if you're not familiar with Zoom, most of us are by now, with the pandemic going on, either from work or just family. Please keep your video and your audio muted. The bandwidth can sort of be a difficult situation at some point. But you'll be able to hear us, of course, and Dr. Elinor Gates talk as we go through. So we're going to have Elinor present her talk this evening, and then afterwards we'll either open up a chat room or we'll have there's a little feature in Zoom called Raise Your Hand, and we will have all the questions after the talk, not during the talk. It's just a little too distracting to do that type of thing. So I wanted to give you a little quick rundown of the Peninsula Astronomical Society, which I'm a member of. I've been a member since my days in high school, 1976. They were formed in 1949, big group of just about 10 people. Mostly from Stanford Research Laboratories, and Stanford University started the club. Terry Terman is one of our current board members. He's the son of Frederick Terman, a very famous Stanford alum there, of course. And so since 1949, club's been in operation. And about 1965, one of our members, Marv Van, built and donated a telescope to Foothill College Observatory, which was there for many, many years until about 1998. 16-inch f6 Newtonian reflector that he built that was housed at Foothill College. And I had the pleasure of using that telescope from about 1969 until we decommissioned it. So at Foothill, the current telescope we're using is a modern Meade 16-inch f10 telescope, computer controlled, much easier to use for the public. We could actually click and point at any object you want in just a matter of seconds. So Foothill College Observatory, unfortunately, of course, is closed at the moment, but keep us in mind for your future astronomy meets when the COVID things wind down. And it's a wonderful site. Little bit in the lights, of course, but we actually do really well up there. We get cameras on the telescope. We're training staff all the time up there. We work with the Foothill College staff, and we do classes with the astronomy department up there all the time. It's a lot of fun. So one other thing that our club has, which is actually very rare for a club in the area, we have about a half an acre of land with 2 observatory domes up on Skyline, very close to Castle Rock State Park. It's a private site. It is, you have to be a member to be able to use the site, and there is an additional use fee. It's $18 a year. It's like, that's almost nothing to actually be able to access the site. And it's a wonderful site up at 2,400 feet above sea level. We're normally above the local fog, and it's an amazing place. And we've been keeping that operational since about 1967 is when that observatory site became available to the club. So our current club roster is about 180 members. Again, we normally operate out of Foothill College Observatory and the Foothill campus there for our classes and our monthly meetings, but we've had to defer that, of course, for now. So that's a little bit of the club information. We are actually, if you are interested in becoming a member, our website is pastro.org. You could join to be a member right online, right there with a PayPal account. And if you are interested in the Oak Ridge Observatory, you do have to be a member as well. And we handle that a little bit more offline, where you have to send in a disclaimer and payment for that through the old snail mail U.S. Postal Service, which is being refunded right now, I hear. So we'll see how that goes. But if you're interested in Oak Ridge, please contact me. I'll actually give out my email address. It's rickbaldridge.com Comcast or at Comcast.net. And it's also on our club website in our newsletter. Second page lists all our board members. So at this point, I'm going to actually turn this over, and our co-host for this evening is our PAS website master and board member. His name is William Phelps. He's going to take over some of this operation for this evening and help Dr. Gates with her talk this evening. So let me give you a little bit of an introduction to Dr. Elinor Gates. We all call her Ellie. I know she likes that, of course, but Dr. Elinor Gates is one of two staff astronomers at Lick Observatory. She does get an opportunity to do some of her own research up there, but she is a world premier expert on laser guide star adaptive optics, which she has done amazing things with, not only up at Lick, but with the Keck telescopes in Hawaii and other places. She has had the honor to have an asteroid named after her, actually a very low numbered asteroid, which is amazing. That number 2650, Elinor, is the name of her asteroid that she has named after her. And I've had the pleasure of being, she's my boss, actually, up at Lick Observatory. I'm a volunteer up there, actually a telescope staff member. And she does a number of amazing things at Lick Observatory, not only the only research and keeping the telescopes operational, getting grad students and students trained up at the observatory, but she handles the public program. She handles the volunteers. She handles, getting the concert series that some of you are aware of up at Lick Observatory. She does that all in essentially her spare time. So I do a big bow to Ellie for doing all those things, which unfortunately had to be canceled for this year. But she does a lot of things behind the scenes at Lick Observatory that just most people don't appreciate or don't even know about. And I'll tell you, I appreciate it. She's also a very, very talented singer. She does plays here in the local area, San Jose, Santa Clara, San Mateo. And I tell you, Ellie, I'm going to probably blush at this, but the one time I heard you sing in the dome of the 36-inch refractor and your voice in that dome resonating like it did, I will never forget that for the rest of my life. So that was unbelievable. That was awesome. So I'm going to turn the talk over at this point to Dr. Elinor Gates. Her talk this evening is Lick Observatory in Pandemic Times, 1918 to current 2020, and we'll see how it. Thank you for joining us tonight, Ellie.
Okay, thank you very much for that lovely introduction. And let's see if I can actually get this share from beginning. Okay, with luck, you are seeing a big full screen image of my opening slide. And you can hear me okay. But I thought, given our current challenging times and my interest in both the history and science of Lick Observatory, that it would be interesting to research how Lick Observatory was affected by the pandemic in 1918 with the Spanish flu, and how that compares to how we're dealing with the current pandemic with the coronavirus and COVID-19. But before I get into that, I'll just give you a little review of Lick Observatory itself. For those of you that don't know, Lick Observatory sits on Mount Hamilton, the highest peak in the Bay Area, east of San Jose. So it's about an hour drive up a very windy road to get to our observatory. And we have many, many research telescopes on the mountain and a few telescopes that are retired. So you can see many of them are labeled. Not all the telescope domes on the mountain are in this picture, but you can get an idea of how busy a facility we are during regular times with lots of research and public programs going on. Lick Observatory origin starts with Mr. James Lick. He was a Pennsylvania businessman, and through a very long and interesting story, which warrants its own hour-long talk or more itself, became the richest man in California through real estate investments during the California gold rush. And he amassed a fortune of over $3 million. And he wanted to build a monument to himself so he would be remembered. He had many ideas, which I won't go into, but my favorite was a huge pyramid in downtown San Francisco, bigger than any in Egypt. Fortunately, saner and more practical heads prevailed, and people such as George Madeira, an itinerant astronomer, said to James Lick, if I had your money, I would build the greatest telescope in the world. And that idea stuck with him. And so he eventually decided to take $700,000 of his fortune and build the greatest telescope in the world. The telescope he built was the 36-inch Clark refractor. Sadly, he did not live to see the construction of his monument. He passed away in 1876 and was buried in San Francisco while they were just starting to construct the road to Lick Observatory. However, when they were nearing completion of the telescope in 1887, they disinterred James Lick from San Francisco and reinterred him at the base of the pier of the telescope. So the telescope today is quite literally James Lick's tombstone, and a suitable monument to him. It was also proven to be very soon after it came into operation. It was the biggest refracting telescope in the world at the time, and they had scheduled January 1st, 1888 for their first light party to look through the telescope and see its true worth and value for astronomy. Unfortunately, the weather was poor, it snowed, so they had to wait till January 3rd when the workmen were able to clear enough snow off the dome to open the slit. Unfortunately, they couldn't rotate the dome, but they were able to calculate that, Aldebaran, brightest star in the constellation Taurus, would be visible so they could check how well the telescope focuses and sees the sky. Unfortunately, not all went well. They looked through the telescope and realized it couldn't focus, and they determined that an error had been made in measuring the focal length, and the telescope was actually 6 inches too long. So over the intervening time, while the weather closed back in with more snow and ice, they actually fixed the telescope, and on January 7th, James Keeler used the telescope for science for the first time. And he looked at Saturn as the first scientific object through this telescope, beautifully in focus, and he discovered a new gap in the rings of Jupiter. And he dubbed it the Encke division, or Encke gap, in honor of another astronomer. Later, when Voyager discovered a new gap in the rings of Saturn, they named it the Keeler gap in his honor. But immediately, on the first night the telescope was used for science, they made a great discovery. Of course, other great discoveries were made in the early history. Edward Emerson Barnard, who most of us know from Barnard's star, which is one of the highest proper motion stars in the sky, he discovered Amalthea, Jupiter's fifth moon, and the only moons of Jupiter known before that were the 4 discovered by Galileo about 300 years previously. So you can see these scientists at that time made very careful drawings of their observations. Photography was a brand new thing in astronomy, but Amalthea was the last moon in our solar system discovered visually, meaning that an eyepiece was used to discover the moon rather than photographic techniques. Another important area of research right at the beginning of the observatory was looking at the moon. There wasn't actually that much known about the moon yet, and so Edward Holden, our first director, was busy, he and his staff were busy taking pictures of the moon at different phases. And along the terminator, you get very high contrast images of the mountains and the craters and everything. And he wanted to take all that information along the terminators, combine all those images to make an incredibly high contrast, detailed map of the moon. Now, he never quite finished that job in the time he was at Lick Observatory, but the moon images were used in textbooks and still used in textbooks today because they were so wonderful from the 36-inch. But just earlier this year, Andrew McCarthy, an amateur astronomer, essentially did the same thing with modern technology, creating this absolutely beautiful high contrast image of the moon showing all its details. And I'm sure Mr. Holden would have very much appreciated that science. Anyway, we're now going to move 30 years into the future from the observatory's founding to 1918 and the Spanish flu pandemic. Really, the Spanish flu pandemic in the United States started when the United States entered the World War in April of 1917. And because the Spanish flu started in Europe. And by June 1917, they were drafting young men because they needed more soldiers for the war. And those soldiers went to Europe, were exposed to the Spanish flu, and of course brought it back with them, as well as all the support staff and the nurses and the everyone that had been helping with the war. So that by March of 1918, there were the first outbreaks of the Spanish flu, and they weren't very big at first. Just like they weren't that bad back in March of 2020 this year, which seems like a lifetime ago. But by September of 1918, the second wave of the flu hit, and that was the truly devastating thing. There were 14,000 cases of the flu just at Camp Devens, an Army base outside of Boston, or a military base, I think it was Army. But people were being isolated, and they were trying to contain it. And by October of 1918, they had 195,000 Americans die just in that one month. There were shortages of medical professionals and nurses. Cities were using cold storage houses because the morgues were full. Schools were closing in Chicago and other cities. Movie houses, public gatherings were prohibited. San Francisco was requiring anyone that worked with the public to wear masks and recommended it for everyone else. It sounds very scarily familiar to what we've been going through. So these are tried and true techniques to contain a pandemic. Of course, in November of 1918, the World War I ended, but that enabled a resurgence of the Spanish flu because all of those soldiers in Europe were coming home and bringing the flu with them. And so the third wave of the flu hit in January of 1919. And just in San Francisco alone, there were 101 deaths reported for the first 5 days of January 1919. It was very, very quick. In the US, things started abating in February of 1919, but our president went to the peace conference in Versailles in Europe, and he collapsed. And they think it's because he was weak from influenza, which was still rampant in Paris and other parts of Europe. So it was not over even by the middle of 1919. And the grim statistics are that the worldwide death toll, they believe, for the Spanish flu was somewhere between 20 and 50 million people. Now, put that in perspective, the population of Earth, of the whole human race at that time, was on the order of 1.5 billion. And of course, we have over 7 billion people on the planet today. So it was a huge number of people affected by the pandemic. So how was Lick Observatory affected by this? Well, Lick Observatory was a very different place back in 1918. So where my cursor is going up and down, that's what the area we call downtown, Mount Hamilton, right there in the middle. And essentially everything east or to the right of that spot that's on this map from Google Maps didn't exist back then in 1918. That's all more recent construction. There were buildings over there, some barns, workshop sheds, a few houses, but they don't exist anymore. To the west, there is more resemblance to what the observatory looks like today and back then. So, the main building here with the 36-inch Clark refractor that James Lick had built. There was a 12-inch Clark refractor at the other end of the building. This building right here didn't exist. That was the lab and measurement building. In that spot was a meridian circle transit instrument. And you can see a picture in the lower left-hand corner there of that. And that's, remember that because it'll be mentioned in a little bit again. There are also other, the Crosley Telescope Dome was installed in the 1890s. And there are a couple houses that were built in 1894 that still exist. Edward Emerson Barnard lived in that one. William Wallace Campbell, who later who was the director of Lick Observatory in 1918, is there. In fact, I'm broadcasting to you today from the old director's house Just so you know, I am here on Mount Hamilton at this moment talking to you. Anyway, but that's what it looked like. And it found out with all the research I was doing that the Spanish flu pandemic the disease itself did not particularly affect Lick Observatory. Lick Observatory was so remote at that point. Back in 1918, only one family on Mount Hamilton owned an automobile, and that was the director, William Wallace Campbell. Everyone else either got their groceries, they ordered them, and they came up on the Mount Hamilton stage, or it came through the mail. They didn't go down to town very often, so they were isolated. So to the best of my knowledge, no one on Mount Hamilton actually ever came down with the flu. What really affected Lick Observatory was World War I. The younger astronomers and the students, many of them were drafted and they had to go to war. And many of the technically skilled people, such as Heber Curtis, who will be mentioned a few times later in the talk, volunteered to help with the war effort, so that he was using his technical skills to help the war effort and help the war end sooner. So that many of the younger astronomers were not available on the mountain. And those roles, either things didn't get done or those roles were filled by some of the female astronomers and lady computers who were, would still operate the telescopes and help analyze the data. So what were the hot research topics in 1918? Well, the biggest topic was the total solar eclipse visible from Golden Dale, Washington. And back then in 1918, because people weren't as mobile as they are today, there weren't any travel bans that I'm aware of, so that they were fully able to go travel to the total solar eclipse and set up. They set up their equipment about 400 feet north of the eclipse central line. They were on a nice farm that allowed them to set up camp there. And of course, the big science topic was, how do we prove Einstein's theory of general relativity? And one of the best ways to prove this is to look at a total solar eclipse. And the sun's gravity causes light from the stars, more distant stars, to bend. Now, if the sun is visible, of course, it's so bright you can't see the stars. But when the moon moves in front of the sun during an eclipse, it becomes dark enough that you can see those background stars. So the idea was to take photographs during the total solar eclipse and measure very accurately the positions of all the stars they could see in that frame, and then compare them to photographs of the same area of the sky taken 6 months previously at night, and see how much the light of those stars was deflected by the sun's gravity. Now, Heber Curtis had these lovely glass scales constructed to make the measurements, and these are still in our Scientific Objects Archive here on Mount Hamilton at Lick Observatory. And Heber Curtis was actually such a prominent scientist, and this was such an important research project. He was actually allowed to take leave from his War Department job to come take data about this eclipse. Unfortunately, things did not go well enough for them to actually confirm Einstein's theory of relativity during this eclipse. They were plagued with two problems. One, the weather. It was very cloudy right up until just before the eclipse, and then the clouds cleared, they got a few exposures, and then right after the eclipse, the clouds closed in again. So they didn't get the data they really wanted. But what really hampered them was that most of their equipment actually didn't make it to the United States in time for the 1918 eclipse, because they had tried this experiment 4 years before, in 1914, in the Ukraine, where there was another total solar eclipse. And unfortunately, that total solar eclipse was also weathered out, but that's also when World War I started. And so all of a sudden, the German members of their team were arrested in Ukraine and Russia and put into prisoner of war camps. The Heber Curtis and William Wallace Campbell and the rest of the crew were originally scheduled to go back to the United States through Germany. They actually had to take quite a circuitous route going through Finland because of the war, and they couldn't bring their equipment with them. They had to leave their equipment in the Ukraine with some trusted colleagues. And because of the war, they just couldn't get that equipment back to the United States in time. So they did the best they could. They borrowed some lenses from Chabot Observatory, which is local here in the Bay Area as well, and did the best they can. But the equipment just wasn't quite up to the task, even though they had a small window in the weather to get data. So unfortunately, they were not able to confirm Einstein's theory of relativity. The next year in 1919, Eddington did get preliminary data, tentatively confirming general relativity. And then in 1922, William Wallace Campbell and Lick Observatory astronomers went to Australia and really definitively proved that yes, general relativity happens. It explains that they saw the bending of light from the star measurements at a total solar eclipse. It was wonderful. But that wasn't the only research they were hoping to accomplish. So it wasn't a completely wasted trip to Washington. Mr. Tucker had been using the meridian circle to measure very accurately the moon's position. And he realized that the nautical almanac's prediction for when the eclipse would happen was off by about 20 seconds. And it would actually happen 20 seconds or so earlier when totality actually occurred and they had very accurate clocks and timing information. They actually determined that, yes, he was right. The totality began 16.6 seconds in advance of the almanac prediction. So Mr. Tucker was very good at his job. They were also doing some early work studying the sun's corona. A lot was not known about it, both looking at the coronal spectra and its polarization. So to take a spectrum, typically you use a diffraction grating, sort of like acts like a prism. It spreads the light out into all its component colors. And they had a very high resolution diffraction grating with over 14,000 lines per inch to spread the light out more than previous spectrometers could. And if we look at the spectrum here, the lower one here where my cursor is moving is the solar spectrum. And you can see absorption lines, both from the Earth's atmosphere and in the photosphere of the sun itself. And then above it is the corona spectrum for comparison. And you can see this line here is just the continuum emission, but then there are bright spots that correspond to certain emission lines, like hydrogen emission here, the hydrogen beta line, and you know, many other hydrogen lines, as well as helium and calcium in there. So, you know, and they were able to identify many lines. They didn't know what caused some of the lines. And one of the biggest conundrums was this bright line in the lower spectrum called the green coronal line. And we still call it that today because astronomy loves history and you know, we have a good name for something, we tend to stick with it. But one of the accomplishments of this total solar eclipse is, one, the green coronal line was very visible. It's not always there. And two, they were able to get the most accurate wavelength measurement ever. So they determined that it wasn't really at 5307 angstroms wavelength, it's actually at 5303 angstroms. But they didn't know what element caused this line. And these little hashes above and below the spectrum is actually iron comparison spectra, so that they could figure out what wavelength this line was. So today, of course, we have figured out that the green coronal line at 5303 angstroms is actually caused by very, very highly ionized iron in the corona. And of course, they just didn't have the technology to ionize iron that extremely back in the 1918. Now this is a spectrum from the 2008 total solar eclipse, and you can see that green coronal line is almost non-existent, whereas it's very easily seen back in the 1918 eclipse. We don't quite understand why it's sometimes visible and sometimes not. That's one of the things we're still studying, but at least today we know what element causes it. Another aspect was looking at the polarization of the corona. So they took pictures in both green and blue light of the solar corona using a calcite cube to split the polarized light into the two polarizations. The calcite cube, as you can see in the double image in the picture here, one polarization will end up in one image, the other polarization in the other. And you can actually compare the two relatively easy and measure the polarization. Now, polarization of light in our day-to-day experience happens when light bounces off something, say reflects off the pavement or water or snow. And that's why our polarized sunglasses work so well, because that polarized light, if you align the polarized of the sunglasses in the other way, it blocks that polarization, gives you a clearer view, less glary view when you're out and about. So they determined from these data that the blue images were somewhat greater polarization than the green images. That's very characteristic of scattered light, that the shorter wavelengths scatter more than the longer wavelengths. So the blue would scatter more than green. And they also determined that this scattering was happening by particles more than 800,000 miles from the sun's limb. So they actually could figure out where the scattering particles were. They didn't know at the time what those particles were, but it was a fundamental research. So that was the sun. They also studied other stars at that time in 1918. One of the big projects was that the Mills expedition, which was actually sent to South America, to Santiago, Chile, where they set up a 36-inch reflecting telescope with a spectrograph. And one of the big topics was looking at the orbits of binary stars, two stars, or spectroscopic binaries, two stars. So spectroscopic binaries, you don't see two stars, but you see the spectra shifting as one star goes around the other, as they orbit each other. So A Carinae is a G5 star. So I've got some sample spectra here, so you can see the G5 star. Our own sun is a G star, so it's not so different. And you can see these dark lines. Those are where certain elements and molecules in the star's photosphere are absorbing light. And when you have one star orbiting around the other, when it's moving towards you, those little dark lines will shift to be a little bluer in color. And when it's moving away from you in its orbit, it'll be a little redder in color. So this is what we call the Doppler shift. And they wanted to measure this very accurately and measure those changes in velocity to an accuracy of 1 kilometer per second. Now, this is not an easy thing to do. 1 kilometer per second is a very tiny measurement. Just to give you a sense of scale, 25 kilometer per second velocity will give you about half an angstrom shift in wavelength. That is something your eye cannot discern at all. So these were very, very careful measurements. And with A Carinae, they got this, they measured it over a couple years. And you can see this absolutely lovely, plus or minus 25 kilometers per second measurements. So these are tiny shifts in the spectra. But you can see it's an absolutely perfect sine curve, which means that it's actually a circular orbit of these two stars orbiting around their center of mass. So they determined the period to be about 195 days, perfectly circular orbits, really nice. Not all stars are so well behaved with nice circular orbits, like Data Columbae, which one has a very longer period they measured of 870 days, but it's a highly elliptical or highly oval orbit. So you can see here, and also the change in velocity with the orbit is much smaller. It's only 25 kilometers per second from peak to peak here. So even more difficult to measure accurately. But you can see as it's going up here, the star is sort of moving, going out the slow part of its orbit, and then it gets close to its companion star and whips around it, shoom, and then goes back out again. Very elliptical. Most stars do not, most binary stars don't have quite so elliptical orbits, or at least they didn't think so at the time. We still don't know. We're still working on statistics on orbits of binary stars and how common they are. But very interesting work. So lots of stellar work going on. They were also doing solar system work. 1918, Comet Shore was discovered, and by a astronomer in Germany. But astronomers at Lick Observatory, so Mr. Aitken, who later became director of Lick Observatory, made measurements. Also, Edward Emerson Barnard made measurements, though he was no longer at Lick Observatory. He had moved on to Yerkes in Wisconsin with a slightly larger refracting telescope. But anyway, they were able to determine the orbital parameters of this comet. So it has a period of only about 7 years. So it comes around pretty frequently, but it's never very bright. It's pretty small and never gets particularly close to the Earth or the sun. So it's not one of those spectacular ones that we look at very frequently. Certainly not nearly as spectacular as Comet Neowise in my background picture. Also, they were looking at the orbits of asteroids. There are many asteroids in our solar system. Of course, in the past couple decades, hundreds of thousands have been discovered. Back when I was working at the Minor Planet Center, there were only about 4,000 named asteroids and some tens of thousands others that had been discovered. 718 Iridia was discovered by Leuschner, and he in 1911, and he named it after his daughter Iridia, because at that time, discoverers had first dibs on naming the asteroids they discovered. But most of the data on this asteroid were actually taken by women astronomers at both Maria Mitchell Observatory and Lick Observatory. And they refined and calculated the orbits. Most of those calculations were done under the auspices of Mr. Jeffers at Lick Observatory, who was managing a lot of the science programs at the time. Now, today we know Iridia is a fairly large asteroid of a diameter of about 36 kilometers, but they didn't know that back then. They were just trying to figure out how quickly it orbited. And with 5.3-year orbit, that puts it very firmly in the main asteroid belt with most of the known asteroids at that time. So one of the other big pieces of research was extragalactic, though they didn't know it was extragalactic at the time. This was leading up to the great debate between Heber Curtis at Lick Observatory and Harlow Shapley at Harvard College Observatory. And they were debating the nature of these spiral nebulae. And you can see a few in this picture. Heber Curtis is here on the left, Harlow Shapley on the right. James Keeler, who sadly died young, and he was not alive in 1920, and Heber Curtis were noticing that in all the photographs they were taking with the Crossley telescope at Lick Observatory, that if they weren't looking right at the center of our galaxy or the disk of our galaxy, they were seeing lots of these fuzzy nebulae, spiral nebulae in the background. And there were just so many of them, and there was a debate. Are these part of our own Milky Way galaxy, or are they much further away in other island universes, because they hadn't coined the term galaxy yet? And Heber Curtis was firmly of the opinion that the data and distribution of these objects was definitely, they were outside of our own galaxy, whereas Harlow Shapley just had a hard time believing the universe could be that big and house other galaxies in addition to our own Milky Way. Of course, it turns out Heber Curtis was correct. And that these are distant galaxies and that our universe was much vaster than they had previously realized. So now, that was in 1920. Now let's motor forward to today in 2020. I'll give you a short pandemic timeline. So I won't mention everything mentioned on these slides, but just note that the stuff that's highlighted in red are the things that affected Lick Observatory directly, or our administrative offices at UC Santa Cruz. So it's very local as opposed to the bigger picture. But the whole COVID-19 pandemic really started in Wuhan, China, where they reported a cluster of unusual cases of pneumonia. And a week later, roughly in early January, they identified it as a new novel coronavirus was the cause. Now, coronaviruses are actually very common. They cause the common cold, but they also can cause serious diseases like SARS. And this, unfortunately, is one of the dangerous ones. And in fact, much more dangerous and devastating than the SARS outbreak in 2003. But the first known death from this new disease was on the 11th of January. And of course, it spread to the United States. By the end of the January, it had been, the WHO had declared a global health emergency. After about a week into February, the death toll in China from this new disease had surpassed the total number of fatalities from the SARS outbreak. So it was very, very worrisome. And just on the 11th of February, the WHO gave this disease an official name, COVID-19, that we're all now very familiar with, caused by the SARS-CoV-2 virus, as opposed to the one that caused the SARS pandemic or epidemic beforehand. By the end of February, we had our first recorded death in the United States from this disease. By early March, the global number of cases had reached 100,000. So it was clearly this was escaping any control. It was going to become a major factor as cases were popping up all over the world at this point. By the 11th of March, UC Santa Cruz decided it was prudent for the safety of their students and their staff to suspend in-person classes. So all our astronomy faculty all of a sudden had to change how they were teaching and move to this remote instruction using Zoom and other techniques for keeping students involved and educated. On March 12th, we here at Lick Observatory said, we need to protect our visitors. We have a visitor center that's open to the public. We have showings of the historic 36-inch telescope. And we decided we needed enhanced cleaning standards. We'd reduce the size of the groups going into the 36-inch so that people could spread out, keep their distance from each other, et cetera. We also realized that there was no way we'd be able to have events because all our events are more than a few people. So we had to cancel all our April and May events, which included a few weddings as well as public evening tours and other activities that we have open to the public here at Lick Observatory. Of course, by 13th of March, many states were announcing plans to close schools to protect the students and the staff at those institutions. And so just, the next day, the 14th of March, Lick Observatory, as well as other museums in Santa Clara County, decided that it would be wisest to close to the public. It's just too dangerous. We don't understand enough about this disease and how to prevent it, how to treat it. Best to just shut down and keep people safe. A few days later, Santa Clara County and Lick Observatory is in Santa Clara County, so that's the county I'm going to focus on here in California because this is where we are. Had started its shelter-in-place order, and of course the rest of the Bay Area followed suit about the same time, though Santa Clara County was the first. UC Santa Cruz decided to close its campus to all except essential personnel and activities. That meant that we had to ramp down all our research. If we were working on research programs in the lab or technical shops at UC Santa Cruz that support Lick Observatory, we had to figure out how to ramp those down so that we didn't waste the work we had already done, keep our equipment safe, et cetera. So it was a very stressful, challenging time to figure out how to do this and what was essential and what wasn't and make those decisions. By March 20th, the whole of California was issued a stay-at-home order to try and protect people. And at that time, there were only 1,000 cases in California, but New York City had many, many more. So it was clearly the epicenter of the outbreak in the United States. By the end of March, there were over 500,000 cases in the world. And by early April, the number of cases in the world was over 1 million, and the US deaths had increased to over 5,000. New York City, or the New York State, I mean, had over 150,000 cases. That was more than any other country in the world at the time, except for the United States. And clearly, this was not going away. I had to make the very painful decision, because I'm very much an optimist. I had hoped that things would get better quickly and we'd be able to still have our summer programs, but that just wasn't possible. So I had to cancel all our 2020 summer events, including all our concert series, speakers, everything, including private parties and weddings and other things that were scheduled. So it was really sad. And of course, by the end of April, we had over 3 million cases in the world, and the US cases were approaching 1 million. Of course, we'll skip all the dreadful news to what were the statistics yesterday. Well, yesterday, worldwide, there were over 21 million confirmed cases since the beginning of the pandemic. Now, granted, about more than half of those cases have passed. People either were healed or died. And there have been over 750,000 deaths worldwide from this. Of course, the US is still the world leader in number of cases, with over 5 million cases and over 170,000 deaths. Brazil, unfortunately, is close behind us with over 3 million cases and 100,000 deaths. Santa Clara County, all told, even though the cases are grim, has had over 13,000 cases, but we're doing better than many counties in the United States. And we've had over 200 deaths. Unfortunately, because of reporting problems in California, the last many weeks of data are uncertain. But very grim statistics. So how has Lick Observatory been dealing with this? Well, starting March 13th, the leadership team of Lick Observatory started having daily meetings because the rules and regulations coming out from the state, the county, and from UC were constantly changing. We'd have our 8:30 a.m. meeting, and then by noon or by 5 p.m., something had changed and we had to figure out how to deal with it to make sure everyone was safe. And that has been our guiding principle from the beginning, is make sure that, you know, our staff and the public that are safe and not spreading the disease. So you can see here one of our Zoom meetings. We have Claire Max, our director, Matthew Chetrone, our deputy director, of course myself, Kostas Kloros, who is our mountain superintendent. So he's in charge of all the operations here on Mount Hamilton and the facility. And so we're all sitting, you know, having these daily powwows about who is essential personnel, what's essential, how do we ramp things down safely, what can we do safely and not put our staff at risk. You know, so it was a challenging time. Now we're down to once a week meetings because things have stabilized. We hope it, you know, gets better and that we don't need these meetings, and we can morph the meetings into some other useful group meeting for us. But on March 17th, we had to shut down everything due to shelter in place order and the UC essential personnel only. We tried to enable as many staff as possible to work from home, use Zoom meetings, of course, like everyone else. But our maintenance staff pretty much were essential personnel. We have over 50 buildings here on top of Mount Hamilton. And they all need to make sure that the roofs are good, the water systems work, heating systems, cooling systems, all that works. So they're pretty busy all the time, even though it's, you know, so things haven't changed for them much, except that they can't work together very much because there's a risk of transmitting the disease between staff. Our telescope technicians, most of them were also classified as essential staff because we have instruments that need to stay cold with liquid nitrogen. We have robotic telescopes that actually could continue operating because they didn't require any people in the domes and buildings to go into work. So that they can monitor the weather and the state of the telescopes from home, just going in to do necessary equipment tasks to make sure that our facility does not degrade during this crisis. The most unessential staff at Mount Hamilton actually turned out to be the astronomers. We did not get to go into the telescope domes or do anything. We just got to work from home. Fortunately, there's lots of data to process and things to keep us busy, even during a pandemic when we weren't using the telescopes itself. So as I mentioned already, we had 3 telescopes that were operating because they were automated. The automated planet finder, the Katzmann automatic imaging telescope, and Panoseti. And I'll talk about the research they do in just a couple minutes. The telescopes that had to stop operations were the Shane telescope and the 36-inch Lick refractor, because these required human operators, telescope operators, in the dome facility to move the telescope and make sure everything was safe. So we kept the Shane operator busy by having them monitor weather and monitor the robotic telescopes, and do any necessary emergency maintenance, because unfortunately stuff does break even during a pandemic. Not immune to those normal technical glitches. But there were things that came to an absolute halt. I work on adaptive optics. Rick mentioned that during my introduction. Adaptive optics is a technology that we use to measure how the Earth's atmosphere is blurring our images through the telescope, and in real time change the shape of a mirror to counteract that blurring and give us images sharper than the Hubble Space Telescope. Now, we were in the middle of a wavefront sensor stage upgrade. You can see my colleagues David and Chris here installing the equipment in the lab. And we were just a couple weeks away from going on Sky and having that job done. Had to stop. It was really disappointing. We had some other repairs and new instruments that we wanted to do, and that just came to a complete halt. So that was unfortunate. But what about our robotic telescopes? What were they doing? Well, the automated planet finder is one of our newer telescopes on Mount Hamilton, 2.4 meters in diameter. And excuse me, it's searching for planets around other stars. So you can see in the animation, you have a star and a planet orbiting around it, and that star wobbles It's greatly exaggerated in the animation, but it wobbles back and forth because of the gravitational pull of that planet. So this is very similar to research to what they were doing with the spectroscopic binary stars back in 1918. The concept is the same, but measuring the pull of a planet on a star is much, much harder than it is to find the pull of another star on a star, just because the planet is so much smaller and it's that much less gravitational force. So instead of looking for shifts with an accuracy of 1 kilometer per second, they are looking for shifts in the star's motion, blue and red shifts, with an accuracy of, say, 1 meter per second or better, maybe half a meter per second. Now, any of us can walk at that speed. It's amazing precision. So of course it's much harder, but of course we have 100 years of technology improvements in our favor so that we can actually measure the tug of a planet on its parent star. Whoops, next slide. So as I said, very similar in concept to those spectroscopic binary star work they were doing 100 years ago. The APF telescope is also involved in the Breakthrough Listen program, which is searching for laser signals from extraterrestrial civilizations. We can use lasers for communication today, so why wouldn't another intelligent civilization maybe use that technology to communicate between space probes or spaceships or their planets in their solar system? So they're looking at these spectra that they're already taking for discovering planets around other stars, and many of these stars already have known planets, and we're looking for other planets for other solar systems. So there's a chance that there would be civilization. And the fun thing is that if you have nothing else to do in quarantine, you can actually look at the data yourself and maybe discover that civilization. So you can go through breakthroughinitiatives.org/open data search, and you can go in and enter automated planet finder and start searching. It's not for the faint of heart. It's not, it's not an easy type of research to do, but if you want to dive in, go ahead and do it. All the data are public, and who knows, you might make that award-winning discovery. Also, with respect to discovering other civilizations out there, other intelligent life, is PanoSETI, our newest instrument on Mount Hamilton. We're repurposing the old Carnegie Dual Astrograph dome. So the astrograph telescope is still in the dome, but we've installed these 2 cameras at the bottom of the slit. And it's looking for pulsed laser signals lasting from nanoseconds to seconds that another civilization would create. So what we do is the dome is just parked, pointed south. And we have these 2 cameras. There was first one, and recently the second one was installed. And they've both been installed within the past 10 months. And we open the dome and the cameras watch as the sky moves over them. So they stay stationary, but they have wide field of views. And they're using this cool new technology called multi-pixel photon counters that are sensitive from the near UV light at 300 nanometers all the way through the optical that our eyes can see and into the infrared beyond what we can see down to 1650 nanometers. So it's really fabulous technology. And this is a pilot program. They hope that if this works and they know how to analyze the data, that they plan to make separate cameras that'll be freestanding that survey the whole sky at the same time and place them at various places around the world so that they can monitor the nighttime sky all around the world all the time. And this is run by Shelley Wright at UC San Diego. But we're very excited to have new toys on Mount Hamilton and maybe discovering new things. Our other automated telescope is the Katzmann Automatic Imaging Telescope. It's been automated since about 1998. And at that time, this 30-inch telescope, and you can see my last year's crop of graduate students in the picture of the telescope I took last year. They're all doing all sorts of exciting research now at the various UC campuses. But this telescope's sole purpose is to discover supernova explosions in other galaxies. Back in 1998, when it first became automated, it was discovering on the order of 1 to 2 supernovae a week. And that was more than all the rest of the astronomers in the world combined. Now, of course, that Lick Observatory showed this was a great technique for doing this research. There are many automated telescopes around the world discovering supernovae. But we have changed our tactics so that we're now observing fewer galaxies, but observing them more frequently, so that we can catch that supernova when it explodes much sooner after it happens, so that we can understand more about the progenitor stars and their environment and the early history of supernova explosions. There are two types of supernova explosions. There are the type 1As, shown on the left, that are when you have a white dwarf star and its companion star dumps material onto the white dwarf star, and when that white dwarf star becomes 1.4 times the mass of our sun, it explodes. And when that explosion happens, of course, that explosion could be brighter than the whole rest of the galaxy's stars combined. So they're visible out to enormous distances. But because they always explode at the same mass, it means they're always the same intrinsic brightness. So if you see a bright one, you know it exploded in a nearby galaxy. If you see one that's much fainter, you know that galaxy is much further away. And so we can use these type 1A supernovae to measure the distances to these galaxies. Type 2 supernovae, like the one shown on the right here in excuse me, NGC 3877, is when a star much more massive than our sun explodes at the end of its lifetime, when it runs out of hydrogen fuel in its core for fusion. And these, of course, happen more frequently in younger or in a spiral galaxies where there's more dust and younger stars, because more massive stars tend to live less long. You know, but they're interesting in their own right. So that's some of the astronomy that's continued. Of course, COVID affected all sorts of things. Of course, you can see all our public events were canceled. No Music of the Spheres for 2020. All our film crews, everything was canceled. But in early March, it was clear that our astronomers would not be able to come to Mount Hamilton to observe, and they would not be able to use the remote operations rooms that have been set up at the various UC campuses and certain other universities around the country, like Yale and University of Michigan. So that we decided we needed to spend some of our time adapting and creating what we're calling the pajama observing mode, so that people could observe from their own homes and still get data once we were allowed to operate our other telescopes. So by April 14th, we actually had the pajama observing code ready for our nickel telescope observers. And by mid-May, we had it ready for our Shane telescope. And then we had our Coudet Auxiliary Telescope, the CAT telescope for short, which we started using again in July. So we've slowly been ramping up operations and our science capabilities within the COVID restrictions, and trying to enable more modes while remaining safe. So the nickel telescope, its primary job right now is following up supernova discoveries, both from the Kate telescope and other telescopes around the world. It's mostly operated by undergraduate students, so we were very happy to get this back online and get our undergraduate education mission for our astronomy majors back underway. So, you know, essentially we have one staff member that was going into the dome anyway to fill the scientific camera's dewar with liquid nitrogen to keep it cold. It was simple for him to just configure the filters for a couple minutes and then, you know, make sure the telescope are operational and leave, so that we only have one person in the dome for a few minutes every day. And if something breaks, of course, that's harder to deal with. You know, because we aren't allowed to go into the buildings much, because it's still limited to essential personnel. But this is what some of the data looks like and what the home observing looks like. So if, you know, it doesn't look that much different from our remote observing software, so you can control the science camera here. Here's some data from April, or actually I think it was May, of supernova 2020 HLA. So right above my little arrow cursor is the supernova, and its host galaxy is a little fuzzy thing above it. So that was some of the early data out of the telescope once we got back running. Of course, you can control the telescope here We have video cameras in the dome so you can see what's going on. So it was great. It enabled our students and researchers to get scientific data again from the telescope. Of course, people are a little limited by internet speeds from home. Sometimes things are, your home network isn't as good as you want for science. So it's not perfect, but it's certainly a darn sight better than what we had before. Of course, the Shane telescope, we did something similar. We tested our new software for home observing in the last 2 weeks of May. One of the restrictions with the Shane telescope is that you only get the cast spectrograph, which fortunately is our most frequently used instrument on the Shane telescope. But you can only take spectra with it because we aren't allowed to have enough staff in the dome at the same time working in close quarters to change the instrument. But this is what some of the data looks like. Again, a supernova group, that's one of our major areas. So they were looking at supernova 2020 JFO. And they were actually looking at the polarization of the supernova. So this line that's vertical right through the center here, and you can see its twin over next to it, that's actually the supernova spectrum. And the two copies, one is one polarization, and then the other is the other channel of the polarization. So the way our system is set up, you get two polarizations at the same time when you take data. These horizontal lines in the spectrum, some of them are atmospheric emission lines illuminating the slit. Some of them are absorption lines. That's probably the sodium lamps in San Jose at 589 nanometers. That's probably a mercury lamp spectrum. So we do see San Jose. We wish there were fewer lights there, but we do the best we can. But it was exciting to get data now from our, more of our largest telescope. The Coudet Auxiliary Telescope, unfortunately, is not remotely operable. So if you want to get data from this telescope, you have to enlist one of our support astronomers. And Rick said there were 2 support astronomers in the introduction. Actually, we just recently in May had our 3rd support astronomer on Mount Hamilton start work. So his first project was using the Coudet Auxiliary Telescope to take data of Venus. So we're still doing solar system research on Mount Hamilton. And what they were trying to observe in conjunction with the Parker Solar Probe flyby of Venus in early July was looking for aurora on the dark side of Venus and trying to see the faint aurora and trying to discern that from this mostly solar spectrum caused by solar lights scattered in the Earth's atmosphere or scattered off of Venus's atmosphere is a real challenge. But we were getting data, and Keck and Apache Peak observatories were also getting back online so that some of the other major observatories in the US were starting to take data as well. So, there is a resurgence in operations despite the COVID limitations. Reopening to the public is more challenging. I am in charge of our public programs, and we have a many-phased plan for opening to the public in preparation. Our first phase will just be to open the outdoor areas and have gift shop, curbside shopping. The conditions are not safe enough yet for us to do that. So Lick Observatory is still closed to the public, and so you can't really come visit unless you just want to drive through on a scenic drive through Mount Hamilton. Our gift shop, our online gift shop, however, is functioning. So if you want to support us, you can buy things at our gift shop. Eventually, caseloads will be low enough, and we'll be able to reopen the visitor center when indoor museums are able to open up again. We have a plan for one-way traffic through the building, so we'll have someone monitoring how many people are in the building at the entrance, reminding people to wear masks, etc., and have one-way flow, including through the gift shop, of course, and then out the other end of the building to give people the best experience they can. This is still under development, and we're a long way from being able to open up to the public. Eventually, phase 3, we hope we'll be back to sort of normal operations the way it was before COVID. Who knows if that will ever happen? There's a lot of unknowns. And of course, phase 4 will be resuming our public events when we can finally have group events and large numbers of people, or at least more than 10 in a room at the same time. So this is all very much in planning, and we're hoping we'll be able to implement it sooner rather than later when this COVID pandemic abates What we are doing to keep people involved is we have what are called living room lectures. So the next one is on Monday at 4 p.m. It'll be live via Zoom. We also hope it'll also be broadcast live via Facebook. And if you can't come at 4 p.m., I know a lot of you are working. We will record the event and put it on Facebook and YouTube so that you'll have access to it. But on Monday, it'll be an interview with Alex Filipenko and his experiences and how he's been, so influential in astronomy and understanding supernovae and dark energy. And he's fabulous. If you've never heard him speak, it's definitely worth it. So I encourage you to join that. And finally, I'd like to say, please stay safe and stay healthy until hopefully in the future, I can speak to you all in person in a lovely in-person event. But for the meantime, wash your hands, wear a mask, stay home as much as possible, protect yourselves, protect your family. And also, if you want to support Lick Observatory by buying the gift shop, I have a special PAS 2020 coupon code that'll give you a 20% discount off of items purchased in our gift shop, so you can support us and help keep us going while we have no income from our public events. So thank you for your attention, and I'll open it up to questions.
Okay, Elinor, I just allowed people to unmute themselves. If people want to ask a question, they can either post it in chat, or if you look at your participants list at the bottom, you should have a raise your hand button. And that would be a good way to signal that you want to be unmuted so we can let you talk. Well,
Hi, this is Robbie. I have a question. Is Google sponsoring Lick Observatory operation right now?
So Google has been very kind to us over the past few years by donating money to us for operations. And so that money has been, gosh, I don't even know, but it's more than $500,000. And we've been using it to help fund the salaries for some of our telescope operators and our new support astronomer, as well as buying necessary equipment for the maintenance of the facility and the telescopes. So Google has been very kind to us, and I hope they will continue to support our operations up here.
I see, thanks.
So, oh, I see a question in the chat saying, is everybody C19 free on the mountain? Yes. To the best of our knowledge, no one in our zip code, which is quite large and quite rural, has had any contact with anyone with COVID. So we're all safe so far. So, okay, and there's another chat question. Say, are there any plans to reduce light pollution in the Bay Area? Is there a push for dark sky nights or changing the type of city lights we use? So yeah, it's a complicated issue. Certainly Lick Observatory communicates with San Jose, our nearest large neighbor, about lighting issues. Just in the past month, there have been meetings about these electronic billboards, and that of course can be quite bright and quite distracting. And so we are expressing our concerns, not only about the dangers to the night sky and losing it for research, but also the health effects it has on people, on wildlife, energy conservation. There are many, many issues. They were proposing that if they put them in, that they would be turned off between midnight and 6 a.m. or something like that. So there are compromises that are being floated. A lot of people are against the electronic billboards. In terms of the other lights, San Jose area has been replacing the old yellow sodium street lamps with more modern and energy efficient LED street lights. There are ways that could be improved to be better for Lick Observatory and better for people's health. What they're really going to do for the long term is an open question. I'm not personally involved in that, but the communication is there. So we hope that we'll have some influence in a positive way. So, oh, many questions coming through in the chat. Let's see. What is the protocol if a really interesting optical signal is detected by the SETI initiative? That's actually a really good question. Since I'm not involved in the research, I don't know all the details, but before any announcements would be made, there would be a great deal of checking the work to make sure, is this a real signal? Do we have any terrestrial sources that could be confusing us? Are we seeing any repeat signals from the same place in the sky? And that's pretty much how any astronomical big discovery proceeds, and it go through peer review and such before it ever hit the news services and stuff. But yeah, it'd be pretty exciting if we saw a potential signal, and people would work really hard to make sure it's real and we aren't being fooled by something or fooled by our own wishful thinking. Because scientists are biased too, and we really want to discover something cool and exciting. So, let's see. Not a COVID question, but let's see. What effect, if any, has there been from SpaceX Starlink satellites? Well, some observatories have seen some data ruined by Starlink satellites. I don't think Lick Observatory, at least no images have been ruined yet. Certainly satellites do regularly go through our exposures. The longer exposure you take, the more likely you are to have satellite contamination. Most of the time it's not going through the most critical part of your image or data. Every once in a while you're unlucky, but we also have cosmic rays and other things that can ruin our data. Certainly Starlink is not great for astronomy data collection, and I know the company is working to alleviate some of the problems, but as tens of thousands of these things are launched into orbit, it's going to be a real problem, particularly for big survey telescopes like the Large Synoptic Survey Telescope, which was recently renamed the Vera Rubin Telescope. So yeah, it's going to be a challenge for astronomy, and we're going to have to learn how to deal with it. Let's see. Sorry, trying to see if I've missed any questions. Okay. What citizen science opportunities are available through Lick Observatory or UC? I don't know what's happening in the astronomy departments at campuses other than UC Santa Cruz and Mount Hamilton. So there may be citizen science opportunities I'm not aware of through University of California. Pretty much at Lick Observatory, our only current citizen science project is the Breakthrough Initiatives, Breakthrough Listen program, where you can look at the data yourself. There are certainly other citizen science programs in astronomy through the SETI Institute and the Galaxy Zoo and many other things that are interesting and that I encourage you to do if you're interested, because they're really great programs. So, any other questions? Are you thinking any new telescopes may be built at Lick? Actually, yes, but they're smaller telescopes. Currently, we have in development a half-meter telescope that is going to run a program called PEAS, Planets as Exoplanet Analog Systems. Anyway, they're going to test technology looking at planets in our own solar system to try and understand the data better so that when we look at extrasolar planets and those systems, that we can understand the data and maybe pull more information out. So that telescope, I'm hoping, will arrive on Mount Hamilton sometime in the next year or two. We're hoping sooner rather than later, but everything's been slowed down because of COVID, so it's hard to predict. But that's the newest program that we know will be happening in the near future here at the observatory. So let's see, is Comet Neowise still visible from the top of Mount Hamilton the last few days? To be honest, I don't know. It was really faint a couple weeks ago when I was looking at it and I needed binoculars to see it. I haven't paid attention to it since then because I've been kind of busy with work. So I actually don't know how bright Comet Neowise is at this time.
Awesome presentation. Thank you.
Oh, glad you enjoyed it.
I have a kind of a different question.
Mhm.
Is it possible to attach like a CCD camera and have like online viewing and sort of pretend that you're there, but you can look through it or look at the images? So,
We've been thinking of maybe doing something like that with the nickel telescope. But right now it's being used too much for science and the logistics of our mountain internet, you know, and just trying to prioritize it with our limited staff is a little challenging. But certainly it's another way to get the public involved with the science at facility here at Lick Observatory. So it's definitely one of the things we're thinking about doing, but we just haven't gotten there yet.
thank you.
Okay, folks, hey, if there's no more questions, I mean, we could still leave this forum open for a little longer if you'd like to ask some questions from Ellie.
Yeah,
and
I'm
Shannon.
happy to
But,
stay on the line.
Yeah, no, this was an awesome talk. Really enjoyed it. It's neat to see that Lake Observatory is still at the forefront of science up there. They're adding new equipment and cameras and telescopes and doing some amazing work up there, even during the COVID crisis that we're all facing right now. So real quick club news. So we will not have a September meeting. And the reason for that is the Fall Astronomy Day that's normally scheduled for the entire world really, and International Observe the Moon Night is the same night on September 26th. So we will not plan a regular meeting, and the plan for the Peninsula Astronomical Society right now is to piggyback on a presentation that's being set up through NASA Ames and one of our club members, Brian Day. They're going to do some real-time live feed moon videos and talks, along with some of the moon trek software and things that Brian's been working on for many years. So that'll actually be a lot of fun. I'm looking forward to seeing how that will all work out. So again, no regular scheduled meeting for us, virtual or otherwise, for September, and we will send out meeting notes and links as soon as we get that data available to everyone else. So thanks again, everyone, for joining us this evening. It was a lot of fun. This is, again, something that we're all not totally used to, but this was, getting to hear from a world-renowned astronomer like Dr. Gates and talking to our club has been quite an honor, and it's a lot of fun. Thank you, Ellie, for the talk this evening, and we really appreciate it. And hope you guys, everyone out there, is doing well and safe and keeping cool with the current weather situation down here in the Bay Area. And so we'll talk to you all later in the month. Thank you all very much.
Thank you for having me.
Thank you, Ellie.
Hey, Rick, you still there?
Looks like we lost Rick.
Okay. I'll let things go for a couple more minutes before I shut it down.
Yeah, I was about to say, if anyone has any last questions, they were too shy to say ask with a bigger group.
All right. It was a really good presentation. A lot of interesting stuff. Thank you.
Yeah, I covered a lot of ground.
Yeah.
Maybe not very deeply, but
It's really fascinating to compare the 1918 flu with the current situation. They really are quite comparable in many ways.
it's scarily comparable. And you know, what I also was impressed with was how similar the techniques for doing science were and the topics.
Mhm.
Even though it's been 100 years and the technology has gotten a lot better, the techniques for doing a lot of the measurements have actually stayed very similar.
Wow. Somebody asked if there's a recording available, Gail Weisner. Yes, there will be a recording. It will be up probably on our Facebook page and certainly on our website somewhere.
Okay. Well, I guess no one has any final questions. I guess I will sign off then.
Okay, everybody, thanks for joining us. We're going to shut this down now.
Okay.
Good night.